Greetings, I'm Yinxiang Tao from Tsinghua University. Today I'm going to present our work on BGP path hijacking detection, ARIS, comprehensive path hijacking detection via routing tree. Let's start with BGP hijacking. BGP hijacking is a critical threat to Internet routing security. It occurs when an attacker uses forged BGP announcements to redirect Internet traffic illegally. This can lead to serious consequences, such as traffic interception or denial of service attacks, causing significant economic and security losses. Here are two reported BGP hijacking events in 2022, which caused serious loss. BGP hijacking can be categorized into origin hijacking and path hijacking. In origin hijacking, an attacker announces prefixes not belonging to it and pretends it is the origin. This type of hijacking with incorrect origin AS is well studied currently and can be prevented by methods such as ROV. Path hijacking, however, is stealthier, since attackers use the correct origin AS but forged AS paths in this case. It is capable of bypassing ROV or other detection methods relying on check the origin AS of BGP announcements. This is because in this case, attackers forge an AS path but prepend the correct origin in the end of the path. An example is illustrated in the upper figure, where the attacker ASH forged an AS link with the victim ASV and performed a type 1 path hijacking. A subtype of path hijacking called DEFCON attack or type U hijacking prepends a real path to the victim, making it harder to detect. The lower figure is an example of type U hijacking or DEFCON hijacking. Existing hijack detection methods are not effective against path hijacking, especially DEFCON hijacking. We propose a novel detection method called ARIS. The key insight behind ARIS is recognizing that the hijacking event triggers the formation of a new routing tree for a prefix. Our core idea is to detecting path hijacking by monitoring newly emerged routing tree and comparing it with existing ones in the same origin AS. An example is illustrated in the figure. A prefix routing tree consists of best paths to this prefix observed by a set of VPs, which changes when a hijacking occurs. By comparing them with existing trees in the same origin AS, we can distinguish path hijacking. Furthermore, we validated ARIS performance via various data sources and illustrated that it is effective and efficient. Compared to existing methods, ARIS covers all types of path hijacking and is more efficient and easy to deploy. There are several challenges for applying our basic idea in path hijacking detection. The first one is how to differentiate normal routing changes from hijacked trees. The second one is that monitoring all trees is computational costly. And the last one is normal BGP updates can also lead to changes of routing trees, leading to potential false alarms. Our solution to the first challenge is to design weighted added distance to differentiate routing trees. The solution for the second challenge is to design clustering algorithm to increase efficiency. And the solution to the last challenge is to design heuristic filters to mitigate impact caused by normal BGP updates. The figure illustrates the architecture of ARIS, which consists of route monitor, clustering, and anomaly detector. We define a specific type of weighted edit distance to amplify differences between normal and hijacked routing trees. An example is illustrated in the left figure. The weighted edit distance, or WED, between tree A and tree B includes the cost of deletion of one edge in tree A and the insertion of 3 edges in tree B. Specifically, we assign high weight to suspicious links and impactful links to amplify the differences between normal and hijacked routing trees. Links that appear infrequently in the internet or span large geographic distances are considered more suspicious and get higher weights. This is because these types of links are rare in the real world and are more likely to be forged links. Also, links closer to the origin AS or observed by more VPs have a greater impact in the internet and thus carry higher weight. The definition of WED allows ASes to quantify the difference between trees effectively. For example, in the right figure, the difference between tree A and tree B are considered larger than difference between tree A and tree C, because red links in tree B are considered more impactful than blue links in tree C. Consequently, red links in tree B are considered more suspicious. Detecting hijacking by pairwise WED comparison between routing trees is not feasible because of high computational overhead. To address this, we design a clustering strategy to reduce computational overhead. For example, for a specific origin AS, every prefix belonging to it has a unique routing tree. We firstly merge routing trees with identical topology using a hash function. Then we merge similar trees into a cluster according to a WED and a preset threshold. Specifically, if the WED between two routing trees is smaller than the preset threshold, we merge them into a same cluster. After the clustering, we will only have to compare newly emerged trees with these clusters to detect hijacking, which largely reduce computational overhead of our algorithm. If a newly emerged tree could not be merged into any existing clusters, it is regarded as a candidate alarm. To mitigate impacts caused by normal BGP updates, we designed 4 heuristic rules to filter candidate alarms. These rules mitigates the impact of incomplete BGP convergence, captures typical hijack patterns, and leverages historical routing context. The first heuristic is partial edit distance, which recognizes that the disappearance of edges in routing trees is often part of normal convergence, not necessarily a hijack. For example, tree A and tree B in the figure has large differences, but B is a subset of A. A hijacking cannot likely to cause this type of change. Therefore, when calculating the WED, we ignore edges that disappeared. The second heuristic is size of new cluster. From analysis of existing BGP hijacking events, we found that a hijacker usually targets few prefixes instead of many. So, if a candidate alarm contains many prefixes, it is not likely caused by hijackings. The third heuristic is historical information. We compare the routing trees in a candidate alarm to historical versions of routing trees from the same origin AS for consistency. If the WED between the routing tree in the candidate alarm and the former versions of routing trees in this origin AS is smaller than the preset threshold, then we consider it is a normal BGP update instead of a hijack. Finally, if a candidate alarm is not filtered by these three heuristics, we apply the last heuristic, existing relationships. If a high-weighted link in a candidate alarm is not included in the business relationship dataset, or it violates the value-free principle, it is more suspicious than other links. Therefore, in this case, we consider the candidate alarm a true alarm. We evaluated ARES in various perspectives. Firstly, we collected 12 historical hijacking events and used the historical BGP data during these events as the input of ARES. ARES successfully detected all these past hijacking events we tested against, achieving 100% recall. Importantly, during the detections, ARES had a low false positive rate, generating only about 2.31 alarms per hour on average. Next, we generated hijacking events via simulation across 16 different scenarios, varying the types of the hijacker AS and the victim AS in Tier 1, content, enterprise, and transit access AS. Then we tested ARES on these simulated hijacking events. The results show that ARES achieved high recall in important hijacking scenarios, where Tier 1 and content AS are victims. For exact prefix hijacking and sub-prefix hijacking scenarios, where non-Tier 1 attackers target Tier 1 or content victims, ARES achieved an average recall rate of 97.2% and 99.3% respectively. In this table, there are detailed information of recall rates of different scenarios. Furthermore, the high performance of ARES extended to other scenarios with non-Tier 1 hijackers. When detecting hijacks against enterprise and transit access victims, recall rates are 98.5% for exact prefix hijackings and 97.0% for sub-prefix hijacking. Also, in this table, there are detailed information of recall rates in different scenarios. We also evaluated ARES in other crucial aspects. Firstly, we tested ARES on sampled real-world BGP changes. ARES maintained a very low false positive rate of 1.06%. We also recorded the runtime overhead of ARES when detecting historical hijacking events. Results are illustrated in the figure, which shows that ARES used less than 8 seconds most for every 5 minutes of data. Also, results shows that ARES has high efficiency and low runtime overhead because it took on average only 6.33 seconds to process updates from a rep race collector every 5 minutes at October 2024, demonstrating its capability of real-time detection. In conclusion, we proposed ARES, a novel method for detecting past hijacking by monitoring and comparing routing trees. The key strengths are its full covering of all pass hijacking types, high recall, low false positive rate, and high efficiency. ASes is now integrated in our BGP Watch project, a collaborative BGP routing analysis and diagnosis platform. We are now making adjustments to ASes to better adapt it to real-world application. Thank you for listening. If you are interested in more detailed information, our artifacts are available at the first link, and you can visit the BGP Watch project using the second link.